All right, let's talk about something every molecular biologist has to deal with. You've run your gel, you've done your transfer, and you finally have that beautiful Western blot image. But how do you turn that picture into actual, hard data? That's what we're going to break down today, using a fantastic tool called ImageJ. So you're looking at your blot, right? And you can clearly see that one band looks a little fainter than the other. But is that really enough to publish a paper or draw a firm conclusion? Not quite. The real trick, and what we're going to solve right now, is how to move from that gut feeling, that visual hunch, to a solid, objective number that will stand up to any scrutiny. So here's our game plan. We'll start with the why we even need to quantify in the first place. Then we'll walk through the practical steps, prepping your image, measuring the bands, getting that data over to Excel, and then, the most important part, normalization. And finally, we'll see how it all comes together in a clear, simple result. Okay, first things first. Why are we going through all this trouble? Why can't we just look at the blot and say, yep, that one's definitely lower? Well, because our eyes can totally play tricks on us, and science, demands precision. Quantification takes all the guesswork out of it. It moves you from a vague impression to a data-driven conclusion. It gives you those solid numbers that can truly support or even refute your hypothesis. It's the difference between saying, I think this is happening, and I can show you that this is happening. All right, let's get our hands dirty. The whole journey from image to insight really begins with a clean starting point. You've probably heard the phrase garbage in, garbage out, and it is absolutely true here. Prepping your image correctly is the essential first step. So, once you pop your image open in ImageJ, you might need to invert the colors. We want dark bands on a light background. Next, take a close look. Are your lanes perfectly straight? Probably not. Use the rotate tool to get them nice and horizontal. And finally, play with the brightness and contrast. Your goal here is to kill as much of that background noise as you can, making your bands of interest pop. And now for the cool part. This is where we actually convert those pixels, those little bits of light and dark, into real numbers. The process is pretty straightforward, and it all starts with telling the software where to look. First up, you're going to grab the rectangle tool and draw a box around all the bands in your first lane. Then you just go to Analyze, Gels, and hit Select First Lane. Easy. Now just drag that same box over to the next lane and do the same thing. Once you've marked all your lanes, you go back to Analyze, Gels, and this time click Plot Lanes. This gives you a graph where each band is now a peak. And here's the magic wand. Grab the wand tool, click inside each peak, and bam, ImageJ automatically measures the area under that curve, giving you the raw number for each band. We have numbers. This is great, but they're kind of stuck inside ImageJ. So this next step is super simple, but obviously crucial. We got to get that data into a spreadsheet where we can actually work with it. The number you really care about is the one ImageJ calls area. You can just think of this as the total amount of protein in your band. All you have to do is highlight those values in the results window, hit copy, and paste them straight into a brand new Excel sheet. Okay, let's take a breath, because this next part is, without a doubt, the most important thinking step in this whole process. This is where we transform those raw, kind of meaningless numbers into a real, scientifically valid comparison. So you might be wondering, wait a minute, why can't we just compare the raw area values? I mean, if the treatment band has a smaller number, doesn't that prove my point? Well, not necessarily. And the reason is, we're human. You might have accidentally loaded a tiny bit less protein in one lane compared to another. That happens to everyone. That's where our hero, the housekeeping gene, comes in. This is a protein, like actin, that should always be at the same level in all your samples. It's our internal ruler, our reference point that lets us correct for any of those little loading mistakes. So here's what your raw data might look like in Excel. You've got the area values for your housekeeping gene, actin, and for your protein of interest in both the control and treatment samples. Now, notice the actin values. They're pretty close, right? 8,500 and 8,350, but they're not identical. That small difference is exactly what we need to correct for. So how do we actually do the math? It's just a ratio of ratios, and it sounds way more complicated than it is. First, let's look at our protein of interest. We'll divide the treatment value, 4,500, by the control value, 9,200. That gives us about 0.49. Okay, now we do the exact same thing for actin. 8,350 divided by 8,500 gives us about 0.98. The final step, we just divide that first number by the second number. So 0.49 divided by 0.98.
This little calculation magically cancels out that loading error, giving us the true normalized value.
We've done the math, and now we get the payoff. It's time to take our shiny new normalized data and turn it into a picture that tells a powerful story, one that anyone can understand at a glance.
And this is what it all boils down to: a simple bar chart. Now, by definition, your control value is always going to be 1. The treatment bar now shows its value relative to that control after we've corrected for everything. And here, it's crystal clear. The protein level in our treatment group is about half of what it is in the control group. No ambiguity at all.
And here's where we bring it all full circle. On the right, we have our original image, where we had a hunch that the band was fainter. And on the left, we have the hard data, a graph that proves a nearly 50% drop. We've officially turned a subjective observation into a cold, hard, quantifiable scientific fact.
So at the end of the day, just remember this. The point of all this isn't just to get a number out of our program. It's about understanding the whole process so that the number you end up with is one you can trust, a number that tells the true story of what happened in your experiments.
And that brings up a really cool final thought. Now that you have this powerful skill for turning images into data, what else could you use it for? Think about it. What about all those microscopy images or cell counts or other assays? Where else in your research is there hidden data just sitting in an image, waiting to be quantified?